Good afternoon, everyone. You are welcome to our online webinar organized from IOC project, Software for Exascale Architectures Driven by Hierarchical Storage Management Approach. My name is Kateřina Slaninová. I am a senior researcher at IT for Innovations, National Supercomputing Center in Czech Republic, and my role here today is to guide you through the webinar. This webinar is the first training event of our series of training events to be organized by IOC project in the next almost 2 years. We decided to have this first training event online webinar and to be recorded, to use this as an introduction of the project during the other training events and also for other purposes. The recording will be available to on our YouTube channel of all C projects and also on our website. The webinar is focused on an overall data management and storage platform for exascale computing based on hierarchical storage management and ephemeral data lifecycle management. It is planned to have the webinar for 3 hours. In the first hour, you will hear about the IOC project, the introduction, you will hear the concepts and the challenges, and this will be presented by Philippe Couvet from Atos. After this introduction, we will show you our 5 use cases, which leverage the presented approach from IOC project. Unfortunately, Olivier Ifrik, who was originally announced, is not able to join us today. So the first use case will be presented by his colleague, James Hawkes from ECMWF. And his talk will be about addressing data storage constraints in numerical weather prediction. After him, we will hear Damien Chapin from CEA, and he will present modeling astrophysical system by Ramses. After that, we will have a short coffee break for 10 minutes. I hope that we will be in time. And then in the second part of the webinar, you will hear about our other 3 use cases. We will start with a talk by Jiří Nováček from SATEC. He will talk about remote on-the-fly analysis and cloudification of the cryo-electron microscopy data. After him, Eric Gregory from Ioc Supercomputing Center will talk about particle physics from a supercomputer by UCD. And the last one will be a talk done by Ghazal Tashakor also from Ioc Supercomputing Center, IO Software for Terrestrial Systems modeling modeling platform. Okay, so let's start. The first talk, as I said, will be done by Philippe Couvet from Atos. Philippe Couvet has been working for Atos HPC Research and Development in Grenoble, France for more than 20 years. He's leading a team of 17 researchers and engineers developing products to facilitate data access from large supercomputers. His recent focus is on data-centric solutions that combine cache and acceleration techniques with advanced instrumentation and data analytics. He's also teaching computer architecture and system programming at CNM School. Okay, yeah, so Philippe Couvet will present you the introduction of IOC project, his concepts and challenges. Philippe, floor is yours.
Thank you, Kateřina. Can you hear me well?
Yes, we can hear you. And
okay.
Also we can see your presentation.
Cool. So, so as I just been said, I'm working in the Atos R&D in data management, and for many years. We will go quickly to the next chapters. So first, I want to talk about the context of this IOC project and explain what are the challenges we want to address. So this IOC project is part of, or has two other sister projects that will try to address the challenges and the issue we have with this modular supercomputer architecture. So modular supercomputer architecture is a new architecture or tendency that we see more and more on largest sites, where the machines are no longer monolithic, but are built from many modules, each module with its own computing technology. You may have many cores CPU, you may have nodes with GPUs, we may have new nodes and even new technology to compute, for instance, quantum. And all these modules will be connected together to form the big supercomputer. And the TREE project will try to address the challenges of running applications and workflows on such architecture. So these architecture are very interesting for our customer, for users, because they can update and they can extend the machine very easily, very quickly by just bringing a new module. But they pose challenges in terms of running workflows and application. The main one for I/O, and this is what we are targeting in the IOC project, is that the I/O are grouped in one module, let's say, which is not integrated closely to the others, and so the latency and the throughput from compute modules to this storage module, long-term storage module, is not as high as with the usual and traditional architectures. So this is the challenge we will address in this IOC project. And okay. So what we want to address, or to make it running on this architecture, are workflow and complex workflow, as you will see later in the afternoon. Those workflows will be running on all modules, either simultaneously or sequentially. And the case we want to address is, for instance, when we have one step of a workflow running on one module, producing data that will be reused quickly and immediately by another step on another module. On this picture, you see that it can take some time to push the data to the long-term storage module that will be reused immediately. And so this is, which is not probably optimal. So what is the solution we are designing? First, I will introduce it with three main concepts. First one is this concept of data nodes. The idea is to add data nodes in the architecture that will be located very close to compute nodes, and so will be connected to the modules themselves. And not only to one module, but probably to more than one module to ease and facilitate data transfer between modules when the workflow are running. So those data nodes are nodes that will be allocated as the compute nodes are for workflows. They will be allocated when a workflow is to be launched, and they are equipped with high-speed storage devices such as NVMe disks or even NVRAM to be able to host the data close to the compute, close to the compute resources, to where it's produced and used just after. Second concept we have in the project is the workflow scheduling. So as we'll allocate those data nodes, those resources are limited, and so we have to manage them efficiently. And so as opposed to the way jobs are scheduled on machines with priorities that are not managed at the workflow level, here we want to be able to manage the different steps of a workflow to maximize the use of the data nodes that will be used for them. So to be able, for instance, to have those step one running on one module, producing data on the data nodes that will be reused and consumed by the step two, maybe in parallel or maybe shortly after the step one is finished. So this is the second main concept we have in our solution. And the third one is the link with the multi-tier storage ephemeral storage systems, or long-term storage system. We feel that the POSIX solutions that are deployed today will be no longer meaningful and scalable for such a exascale architecture. And so we were exploring to switching to object storage. And so we have defined this concept of data sets and ephemeral services. Data sets are containers where the users will store their data. And those data sets will be exposed to the workflow when the workflow will be running, when the different steps will be running through those ephemeral services that will be running on data nodes. So the data nodes will run for the workflows, the services that will allow them accessing their data stored in the long-term storage module. So this is the very high level picture of the solution. Now let's have a look at the IOC stack. So the stack will be composed of at the end 2 hardware layers. We have the data nodes, so equipped with high-speed storage devices, which will be ephemeral in the sense that it will be allocated. The resources there will be allocated for workflow when the workflow is started. And we have the long-term storage. It is composed of different tiers. So this is also another point, another focus of the project, which is to develop for the long-term storage, an hierarchical storage management-based solution to be able to unify different technologies, such as so from SSDs, very fast disks, to spinning disk, and also down to tapes. And for that, we will leverage two products that are provided by the partners, the Motor and Cortex ecosystem, which is an object storage solution from Seagate, and the Phobos product, which is again an object storage solution, but storing data on tapes, and that is developed by CM. And so the software stack to run this architecture, storage architecture, will be composed of different layers. At the top, we will have the ephemeral services that will be running on data nodes. So we will have the client part of those services running on the compute nodes. We have the API in between to access the ephemeral IO services running on data nodes. And those data nodes will be able to access the data stored in the long-term storage through the dataset API, and accessing the HSM stack, as I said, composed of the Motor object storage and the Phobos object storage working together, and also bound with other products to manage data transfers and policies and so on. We will see it quickly later. So it's now so this IOC long-term storage module will implement, as I said, a hierarchical storage architecture, leveraging different technology, this Motor object store and Phobos. There will be copy tools in between to move data from one layer to another one. There will be also smart data placement strategies that will be developed in the project, but it's probably not our focus today. And so everything is stored in this long-term storage module is exposed through using the S3 protocol. So S3 has been chosen because it's standard. It allows to manage many aspects such as user management, access rights. It allows to store many attributes to objects stored. To the objects, and so that's why we chose this protocol. We will still have a native API access for very fast transfer when it's needed, but the main path is through the S3 server. And we also have a plan in the project to develop a solution to import data from existing file system to the IOC solution. Then a few more words about the data sets and namespaces concepts. So as I said already, data sets are data container that are hosting objects. And they could be seen as private file system object stores, because as opposed to the current solution where on the large supercomputer you have many file systems, one or or a few file systems that are just configured and made available to users. They are managed through quotas usually, but they are shared. And so when users need to manage their data, they have to use this shared resource. Here, data sets will be a mean for users to create their own private file system or private object store that will contain their own data, and they will be able to manage. Manage means to move in the storage hierarchy, for instance, but also to configure an ephemeral service on it to get access to it from the compute nodes. So the granularity of the data we propose is the data sets. And for these data sets, we have also invented a new feature that probably is kind of original in the landscape, which is the ability to create many namespaces. Data sets are just a data container, so data are not organized, and there's no, for instance, POSIX organization within data sets. The POSIX organization will be stored in what we call namespaces. And within for one data set, you can create many namespaces that will expose the data stored in the objects through different namespaces that you can use depending on your needs. And on the next slide, it will be maybe a bit clearer with a picture where, for instance, I have my data set here, so an S3 bucket containing some objects. We have 3 of them here, and 2 namespaces. In the first namespace, the object name ABCDEF will be exposed through a POSIX ephemeral service using a POSIX hierarchy containing one directory data and one file name, which is file.txt. And I can have for the same data set, I can have a second namespace which will expose the object one through a POSIX mapping /input/gauge, for instance. So this is offered by the as data sets and separating the namespaces and using or exposing the namespaces through ephemeral services. So now we'll have a look, closer look at the ephemeral services we are targeting in the project. So you have understood that we have the clients, compute nodes, we have data nodes where we have the ephemeral services, and we have the long-term storage. We have seen that this long-term storage is managed as an object store using the Motor object store, Motor server. We'll be able to create on data nodes when it's needed another Motor server, which is an extension of the existing, so that will be that will just give access to the data in the long-term storage. And so this Motor server will be extended with the S3 interface to get this standard interface and manage user authentication and dataset authentication as well. Then, when it's needed, we will be able to configure our ephemeral services on top of this stack on the data node themselves. So first one will be an NFS server that will just expose using a POSIX namespace some data from a data set. And this NFS server will be for when you don't need high performance, because this NFS server is running on only one data node, for instance. And so it's mainly targeted to just give access, kind of interactive access, for instance, to the data sets when the user needs to just look at the data or do some simple processing on them. So this is the purpose of this simple ephemeral service. If you need more performance, then we are integrating a second solution, which is again an NFS server, but accelerated by with a burst buffer solution, smart burst buffer, a product that we are developing at Atos. And this smart burst buffer will be able to run itself on many data nodes in parallel, and so we'll be able to provide the aggregated bandwidth that the application will need to run efficiently. And for that, we need also to deploy the smart burst buffer client library on the compute nodes when the application is launched. So this second ephemeral service is intended for standard POSIX access to data and to data sets when you need high performance. So of course, we integrate also a standard NFS, S3 access as an ephemeral service. So if for some reason the application, the client, the user needs to access their data sets using the S3 protocol, which is supported by the architecture, we will be able to deploy an S3 ephemeral service, which is mainly in such case configure the S3 client environment to be able to access the S3 server that has been spawned for the workflow. So then we have a fourth ephemeral service, which is called DAISY. So DAISY is an innovative library to store scientific data that is developed at ECMWF, and that will be, I guess, presented later in this webinar series with more details. Maybe James will talk a bit about that in his talk this afternoon, but basically you can think of it as a way to store your scientific data by organizing them using scientific keywords. So you can just create your own scientific model using, for instance, cells and parameters, temperature, pressure, things like that. And you can just define the way you want to organize your data. And then the DAISY library will handle everything for you, including the data storage on physical media and the metadata. So it's very simple to use from applications, and integrating it in the Ioc stack, we will handle all the low-level connection to storage transparently for users. So these four services, these four ephemeral services, are the services that gives access to the long-term storage data, so the data sets stored in the long-term storage. And there will be data movements, as you can guess, when the applications wants to access data that are currently stored on tapes or on spinning disks here, for instance. We may want to move the data from those disks to the storage resources that we have configured, allocated and configured on data nodes for this workflow. So when the data are on those on the long-term storage infrastructure, it sits on the shared storage infrastructure, shared disks, shared tapes, shared SSDs. When the data is moved to be used on the data nodes, it's no longer in shared environment, because each resource allocated on data node is only or is allocated for just one workflow, so no longer shared by all others. So in addition to those four ephemeral services that will give access to data stored in long-term storage, as I said, we have also planned for two more ephemeral services, which are those two at the bottom, named SBF, GBF. The names are not very meaningful, but basically it's temporary storage that a workflow can just need. And that doesn't need to be pushed or to be stored in a long-term storage. For instance, if a workflow wants to track or to push some many logs to follow what happened in the applications, but when the workflow has been terminated, those information are no longer interesting and meaningful. You can just create such an ephemeral resource on data nodes and use it for storing those kind of data. And at the end, you just destroy these services, and you don't need to move to push the data and to connect the data to data sets. Just a temporary data for the workflow. And for that, we have two of these ephemeral services. The first one, SBF, is NVMe over Fabrics connection. So it's connected to only one node, one compute node, and it's exposed the resources through an XFS file system. And the second of these temporary service is can be configured to export different things, but basically it exports a parallel file system, such as, for instance, a BGFS. So in this case, if you know BGFS, it's not exactly as the BGFS on demand, because the BGFS on demand is configured on compute nodes themselves using the storage on compute nodes. Here in this case, we just allocate some storage on data nodes, and we configure BGFS servers on data nodes, and then expose only the storage to the compute node using the BGFS protocol. So it's not exactly as the BGFS on-demand solution, and it allows to leverage the high-performance storage resources we have on data nodes. So these are the ephemeral services we will develop in the project. And then I wanted to share an example to illustrate what we expect from this architecture. And so we have run an example, a simple example. It's an NAMD application, computational chemistry, if I remember well. And we have been running this application on a Lustre file system, which is not that high performance. It's 2 GB per second maximum. We have 2 data nodes in the configuration, each with 50 gigabytes and 1.5 terabytes of flash memory, an high-speed network, and 16 CPU cores. The NAMD application itself was running on 12 compute nodes, using a high-performance network, and doing a checkpoint every 3 minutes, 12 gigabyte checkpoints, just to speed up the IO activity. And also this NAMD test case use an input file which is 17 gigabytes uncompressed, that is read at the beginning. And you can see, or you can check, you can get all the details for this use case here. So when we run this NAMD test case on our Lustre file system alone, so no one else using the Lustre file system, we can have it only for us. It takes 1,169 seconds. So it's for 15 runs, it's plus or minus 3 seconds, so quite stable. And if we run the same case, exact same case, but on the Lustre, on generating some noise or some activity on the Lustre file system, so external activity that will consume 1 gigabyte per second, 50% of the capacity, then the same use case is 1 minute longer, and with a more variability on the time. And so we can see here clearly that when we are sharing the IO infrastructure, the IO resources, this affects the time on the application. So it's, I think, obvious, but there are not that many studies on that, and it's difficult to measure the impact and make sure or to size the impact on the compute node. And if we run this same use case using an ephemeral service, so in this case, this is the burst buffer, we save 1 more minute compared to the Lustre alone, because the burst buffer is closer to the compute nodes, is faster because it doesn't handle all the POSIX stuff. And if we measure with 0% load on the Lustre, we have this time. But if we apply the same load on Lustre and run the test case again, we see that we have exactly the same time, or roughly the same time as with no load on Lustre. So it means that we are able to isolate the application from the noise caused by the file system being shared by many applications. In this case, the time that we measure here are not including the time to prefetch the data, the 17 gigabytes of data that the application needs as input, which has been moved from Lustre to the data nodes memory before launching the NAMD application. So it's not counted, and we feel it's fair. It's fair because we can, with our integration, we can create the ephemeral file services, and we can also do the preloading, the data prefetch, before allocating the compute nodes. So the time we have here is really the time that we have allocated the compute nodes, and we have been using them to compute. And so if you compare, it's 2 minutes, 20% or 10% gain compared to the sharing, to the shared Lustre file system. And this, those 2 minutes are 2 minutes where we have not allocated the compute nodes. So it's really something that a solution that allows to maximize the usage of compute nodes because we can do the configuration of ephemeral services in parallel and before allocating them. So this was the last slide for the introduction and principles and concept that we have we are developing in the project. Now I will take some time to focus on the end user interface and APIs we are developing, because to expose those concepts to our users, it will require some new component, new features. And we've been working closely with our use cases to define the solution I will present now. So in terms of user interface, at the end, there are two main pieces. First one is the workflow manager. As you understand, we will manage, we will expose tools to run workflows. And so we have to configure those ephemeral services for the workflow. And so we have to expose an interface to our users to manage the workflows. For that, we have invented a configuration file that describes the workflow the user have to prepare and to fill for us. And then we propose a few command lines to run the workflows, and we will dig into that just after. And second user interface is data management, so data sets and namespaces handling, again with command line tools in the project. Of course, we could develop higher level tools, graphical user interface for that, but it will be probably out of the scope of the project. So for the workflows, we'll look at the user commands we have developed, and we have introduced this notion of session. So a workflow will be run within a session that the user has to start. So the first command that user will have to do is this IOC workflow start command. For that, the user will give us this the workflow description file, the YAML file. We'll have a look at just after, and decide to assign a name to this session, so that then he can have a reference to this session. This allows also to start multiple sessions in parallel if needed for the users. So a session has to be started. Then when the session is started, users will be able to just launch their steps using this IOC workflow run command. At that time, we just need the name of the session that has been defined here, and the name of the step. And the step is described in this workflow description file the user has prepared for us. And the step is one application of the workflow, as you understand. So here the workflow is composed of 3 steps. And then when the workflow is terminated, we just stop the session using this command. So this start and stop command will help the workflow manager will help us to handle the creation of the ephemeral services, and also the deletion when we can release the resources on data nodes. So there are a few other commands that will help our users to handle and to manage their workflows. First one is status. Status display the information about jobs and ephemeral services for one session, for one active session. And the list command, which will list all active sessions of a user. And another important aspect of our solution is the access to the data. that as opposed to the current solution where your data, as soon as they sit in a parallel file system, you can just browse them from the login nodes, because all login nodes are connected to the file system of the supercomputer. In our solution, the data are stored in data sets that are not exposed until you have created an ephemeral service for it. So the data are not accessible. You cannot just browse your data easily. So for that, we have created a notion of interactive access environment that will be also run within a session. So the user will have to start the session, and then if while the workflow is running, the user needs to browse the data, can just launch an interactive access environment using this access command. So basically, this will just allocate a few calls on some nodes and configure the access to the ephemeral services of the session that is targeted. And we can also reduce the services we want to be connected to, adding the parameters at the end of the command. So now we'll have a look at this workflow description file, and you will see it's not very complex, very complicated. There are three sections. First one is a name. So we just want to have a name because in the project we have tools that records the I/O activity of the applications and workflows, and it's convenient to pick the name here in the workflow description file at the beginning of the session. And then we have two main sections in this workflow description file. First one is the services, the ephemeral services. The user just creates the ephemeral services he needs. And as you understand, he needs one ephemeral services per data set that needs to be accessed during the workflow execution. So our users will define how they want to organize their data. They could just decide that for the workflow, they need only one big data set that contains everything. And so in such case, they just need one service. But they could also think to split their data into maybe 2, 3, 4 data sets that will contain different kind of data that are produced by their workflows. For instance, you may want to separate into 2 different data sets your data that are to be kept forever, for long term, and the temporary data that are produced when the workflow is running, such as visualization files or intermediate statistics, that you will not keep forever, or you will just keep 1 week after the workflow is terminated. In such case, it can be a good idea to create a specific data set for that, and then manage data sets to, for instance, delete it after 1 week, and maybe delete it automatically after 1 week. So organizing the data into data set is not something obvious, and we have also discussed a lot of time with our use cases to find the best solution, find what's possible and what's interesting. And something that this is something which is new and needs to be understood and probably iterated to find the best solution. So here, the service we have here is of type NFS. Could be an accelerated NFS, or it could be DAISY or S3. And then we have some attributes to define it. Here, we need to get to know the namespace, or that dataset dot namespace at the end. Which namespace from this dataset needs to be exposed. Then the mount point with where it will be mounted on compute nodes. And flavor, which is an indication of the amount of resources to be allocated on data nodes. So for instance, if I want an NFS server that is just using 4 CPUs and 16 gig of RAM because it's enough for me, I will use the flavor medium, but if I need more, I can use another. So this is a way to expose in a kind of condensed way the resource allocation for services on data nodes. And then the second section is the steps. So the steps are the application to be run within this workflow session. So again, you assign a name, a location, so on which module this step is to be run, and the command to be launched to start this step, and the ephemeral services that are required by this step. So if you have created several or more than one ephemeral service for your workflow, it's not mandatory to configure all services for all steps. So you just list here which one are needed for you. And so when you see this description, you can imagine that when we start the session, the workflow manager will analyze the workflow description file, will check the location of each step and the services they require, and we'll be able to deduce to choose the right data nodes connected to right modules in the architecture to run those ephemeral services. So this is how we handle the placement of the ephemeral services on the modular architecture. So when looking at this file, this first example, we have hard-coded the name of the data sets, hard-coded many things, and it may not be very convenient because it means each time you want to change the data you are processing with your workflow, or each time you want to change something, the main point of your data, you need to create a new workflow description file. So it's probably not that convenient. And so we introduced this parametric workflow description file with variables. So instead of defining the namespace, for instance, you want to use in this service, you just create the variables. And then when you start your session, you just instantiate, give the name of the variables, and then it's handled at runtime. So I think it's obvious how it works. It makes the workflow description file much more generic, and you don't need to manage one workflow description file per run of your workflow, but only per workflow if it's written well. And here we have an example of the status command on a running session where we will see you will see different various information, so name, the session ID, and so on. But it's interesting here to discuss the steps, and we may have pending steps, we may have active steps, and terminated steps. Pending steps, because as you understand, we when a user requests one step to be run, we need before being able to launch the job on the compute nodes, we need to prepare the ephemeral services. And so when the user will ask us, please run this step B of my workflow, before starting the step B, we may have to spend some time to configure the ephemeral services and maybe to move data from the long-term storage to the data nodes. So this is the reason why we have pending steps, because we are not ready to launch the job. We still have to do some preparation to it. Active steps are running, terminated are just finished, and then we plan also to add the status for the ephemeral services, of course, in this command. A few words about this location attributes in the workflow description file. So I already explained that this is how the user can tell us on which module the step will be running. So for instance, the step A will be running on the GPU module. So this wording GPU module is a site specific. Of course, it's defined by the sysadmin when they deploy the solution, depending on their own modules. But we plan also to have a extended syntax, for instance, to allow for applications that are running on more than one module. This is the objective of one of the other project, the Deep Sea project, to extend the MPI ecosystem to be able to run applications, run a single application over two different modules. And for instance, here the GPU and the CPU modules will be used to run this step B. And we plan also in the IOC project to explore the ability to run some steps on data nodes themselves. because data nodes, as you have seen, are allocated for the workflows, are computing resource specialized to handle data, but can also be used to do some computation on those data. And so we plan this possibility to run some processing on data nodes themselves. And for instance, the objective is to implement what we call on-the-fly processing or in-transit processing, relying on the files produced by the steps. For instance, think of an application that produces regularly intermediate results or checkpoints, and you may want to analyze, do some processing on those intermediate results or checkpoint to just verify the application is converging and not still useful to keep running. You can just launch this step C on data nodes because this is where the data are stored. And so this will save moving again the data from data nodes to other compute nodes to do this processing. It will save energy and also time to process. That's why also we plan to add on our data nodes accelerators such as GPUs and FPGA. This is something we already explored in a previous project, the Lexis project, and we plan to continue in IOC and make it available and easy to use for our users. Then another aspect of the control that we give to user is the data mover. Initially, I explained that the user will be able to control and move some data from long-term storage, from tapes to disk, or from long-term storage to space on data nodes. But in some cases, it's not a good idea to transfer all the data sets because they can contain terabytes of data. And if you know that your step will only use a subset of those data, you don't need to move all the data set to the data nodes. And so we provide our users with a means to control these data movements. So we have this trigger that it could be either step start or step stop to indicate if the trigger should be done before launching the step or after the step is finished. And then we provide additional attributes to indicate the target of the move. Should move those data to flash. The operation, which is either copy or move. If you want to duplicate, to create a new copy of your data or just move your data. And then the filter to indicate which of the files should be addressed, should be moved by this data mover. So for instance, you could think of this feature, to, for instance, save very precious results you are producing while your application is running. As soon as they are produced, you want to push them to the long-term storage because you want to have the redundancy, you have to want the RAID protection for your data that you don't have on the ephemeral services on data nodes. So you want to create a new copy of those data as soon as it's produced. It's an example of the use of such of those data movers. And everything we have checked so far describe the user control when the session is active, when the workflow is running. So when the workflow is running, ephemeral services are configured, and so the user can create an interactive access environment, can just browse the data, can change, remove files, or can do whatever he wants with the data. But it's also interesting for the users to be able to control what happened to their data when the workflow is terminated, when the session is terminated. And for that, we provide what we call ints, which are attributes that can be set up and assigned to data. So either at the file level or at the data set level, the entire data set level. Also at the namespace level, if the namespace contains a subset of the data, you can just assign those for the object reference in a namespace. And the hints are, I would say, kind of advices for the storage stack to manage the data. For instance, intended access. So I will access those data, or it will not change, or I will access the estimated lifetime. So I will likely delete those data within 1 month. And you can see estimated access time, access period, predefined policies that we can configure. So these hints are really intended for the user to manage their data lifecycle outside of the workflow execution. So when it's terminated and when the data is stored in the long-term storage. So this is the way the user can control the data management in the long-term storage. And for those hints, again, we will provide user commands to be used. So user command, for instance, to locate to know, for the user to know where is this data set stored right now. Is it on tapes or on flash disks? Of course, users will be also able to move or to copy or to release those data. And they will be also able to set up the hints we have seen in the previous slides using the hints command for their data sets. And we also plan to implement this through the extended attributes of the POSIX files that will be then transmitted to the long-term storage stack, software stack, to just interpret and manage data accordingly. So what we have seen is really the way users will handle their workflow. So run, manage their workflow. We have also a command line interface to manage data sets and namespaces. And here it's probably simpler. Users will be able to create data sets. So using the create commands, we can create a data set and a namespace at the same time, because to access a data set, you understand that you need at least one namespace. Data set must contain at least one namespace. May contain more, but one is the minimum. You can create an additional namespace in it. And then you can for instance, create a new namespace that is empty, and then use this second namespace in a session to populate a data set with new data from a second run of your workflow, for instance. So these are the commands to create namespaces, and then you can also fill namespaces outside of a workflow. So don't need to have an ephemeral service for that. You can just use those commands that to put a file in a namespace. This will help the users to create initial namespaces, for instance, when they just need one or two configuration files to be able to launch their workflow. They can just create an empty namespace, then push their configuration file in the namespace, and then run their workflow that will produce all the data, all the results from this initial file. And so doing so, it enables leveraging the standard POSIX tools and scripting. You can do ls-find in the standard POSIX file system and just push or put the object or the files you want in your data set using scripting. So it's probably convenient for our users. So I'm close to the end of the presentation, and I just want to have a few words about the challenges we have with this approach, which is really innovative. First one is that, as you have understood, we really focus, we really target workflows, and probably the batch manager we have today are not enough workflow aware. We need to make sure when we have allocated that data node resources that it will be used efficiently, and all the other steps of the workflow will be scheduled with an high priority to limit the time allocated, the allocated time of those data nodes. So this is something we have in mind. We are not working on that specifically in the project, but this is something really we have to take into account. And the second one is for this solution to find the right balance between compute nodes, data nodes, and backend storage resources. It's not obvious to decide how much data nodes I need for my machine, because it depends on the I/O activity of your application. You don't know that in advance in all cases. And so it's kind of new dimensional rules that needs to be invented to be able to size such a new architecture and so that it runs efficiently. So that's all I have for this introduction. I hope it was clear enough and will help you to understand what will be presented now by the use cases. Thank you.
Thank you, Philip. Thank you very much for your introduction of the project concepts and for nice examples of user workflows. And now it's time for questions. Okay, so we have one question in the chat from Paula.
Mm-hmm.
It's related to this dataset access. Why a dataset couldn't be accessed by multiple sessions in parallel if it could be in read mode only?
Yeah, so that's a very good question. And I think it was written somewhere in the slide, but I went too fast on it. You're right. So data sets are a container, and as the part of those data they contain are moved to data nodes and are used by a workflow, they kind of create a copy of those data on data nodes that is not up to date if you look at what is in the long-term storage. So we can have newer data on data node. And so that's why we will allow in the workflow manager, we will allow only one use at a time of a data set in parallel. So when the workflows, the session starts, we will check all the namespaces that are referenced in the workflow description file, and then we will take a lock on them, a write lock, so that we ensure only one of those data sets is used at a time.
Okay, we have another one. There is a comment from Jan. Manipulation of file life in seconds is harsh. In the example shown, 26,000.
Yeah, you're right.
Yes.
So these interface as presented are kind of initial shot for the interface, and we will have to probably improve those aspects and propose more than just seconds. I agree.
I think that participants can also ask questions directly now, so you can raise your hand and we will unmute you.
I see Sai also asking a question in the chat about can we connect quality of service ints for data sets and namespaces?
Ah, yes.
Yeah, throughput latency. So I think, yes, you're right. It's possible. It would require additional handling of those ints in the ephemeral services to be implemented in the NFS server or the smart bus buffer, for instance. But yes, it's possible in theory. Yeah, I agree.
And we have another question here in the chat. Shall I read this, or are we able to read the question?
Yeah, a question for Amir. Yeah,
yes.
I agree. The scheduling workflow steps is an advantage of our solution. The workflow manager can do it, but discussing with our use cases, it appears that it's not that obvious. The use cases we have are not, I would say, predictable workflow where we know that step A will run before step B, and then step C and D can run in parallel, and then we can just launch step E. The use cases we have in the project are much more kind of interactive. And for instance, we know we run step A and then B and C, but then we have some manual analysis that will tell if we need to run again some step A, so some more step A. So it's really something that is not in all cases predictable. But there are both. There are workflows where we know in advance what has to be run, and this could be probably scheduled as a big job or with using the Slurm dependencies and things like that. I agree. In some other cases, it's not that obvious.
Thank you. And another related question from Colin: how is workflow error handling managed?
So for the workflow themselves, if you are referring, for instance, to one job failing, as we just are just before Slurm, we just keep the standard Slurm interface to submit jobs, and then we let Slurm manage the jobs with our implementation. All the errors will be managed as usual by Slurm, and the user will get the error message from Slurm, and so we'll be able to react, because as you have seen with this workflow description file, the user keeps control of each step launch time. You can decide to launch step A, then wait for Slurm to confirm that the job has been launched, to then only start the step B, for instance. So we don't replace Slurm. We're just in front of it and integrate with it to configure our ephemeral services at the right time. But we do not replace it, at least in the IOC integration.
Mm-hmm. Okay, thank you. And another question from Giuseppe.
Yes, Giuseppe.
Will this work with more traditional system architectures that do not have dedicated storage data nodes?
Mm-hmm. Yeah, so that's also a good point. You're right. We have done some experiment where, for instance, the ephemeral services are launched on additional compute nodes that are allocated as part of the job. So if my job requires, let's say, 16 nodes, I can just ask Slurm for 20 nodes and use the four other nodes to create the ephemeral services and use them to gather the IO activity and then send it to Lustre and things like that. So it works fine. It's possible to do that. The only maybe limitation we have here is that those compute nodes do not have high-speed storage devices, and so it will be probably less efficient than the data node we have in our project. And they will only use the RAM, the memory to buffer the IO and group them and do the cache. So it's possible, it's working, it's very interesting in some cases, but it's probably not that optimum.
Thank you. And the last question for this topic from Amir: do you recommend someone who is expert in making workflows by regular shell scripts to take time and energy to learn a workflow manager?
Yeah, I think if you have the ability or the possibility to test your workflows on an IOC-enabled architecture, I would say yes. And I think this is also what will do our use cases, and maybe they will present now to transform their standard workflow into IOC-enabled workflow. Yeah.
Thank you. Thank you, Philippe, for your presentation, for your talk.
Thank you.
And now it's time to move to our use cases. So the first talk focused on the first use case will be done by James Hawkes from ECMWF. Addressing data storage constraints in numerical weather prediction. James Hawkes is a computational scientist at the European Centre of Medium Range Weather Forecasts and team leader of the data processing services team. He received a PhD in engineering, specializing in massively asynchronous linear solvers from the University of Southampton in 2017. His current activities revolve around the storage and processing of large-scale time-critical meteorological data, in particular in terms of performance and scalability. He leads, in IOC project, he leads for package 5, driving the development of DAISY, a semantic data management engine for IOC. So, James, you can start.
Thank you very much. Thank you for the introduction. So yes, my name is James Hawkes from ECMWF. This presentation has been prepared by Olivier Ifrig, my colleague, unfortunately couldn't be today, so I'm presenting in his stead. I'm going to talk a bit about our operational weather forecasting pipeline, the developments we're doing inside IOC that are related to it, and finally, how we are using the IOC architecture and the software solutions we're building to experiment with our our weather forecasting pipeline. So first, a little bit about ECMWF. So we're established in 1975 as an intergovernmental organization. We have 23 member states and 12 cooperative states around Europe. And we operate from 3 offices, our headquarters in Reading, a new office in Bonn, and our data center located in Bologna. The main mission of our center is to run 24/7 operational weather forecasts. We run 4 cycles per day, and for each of these cycles, we run 1 high-resolution deterministic model and also a 51-member probabilistic ensemble weather forecast. These forecasts are typically used to support our national weather services around Europe and also to commercial customers around the world. A big part of what we do is research. We have a research department who is continuously trying to improve our models and also doing reforecasts and climate reanalysis to investigate the state of the atmosphere over the last several decades. We operate 2 of the EU Copernicus services, the Climate Change Service and the Atmosphere Monitoring Service. And we're also one of the main partners in Destination Earth, where we operate 2 very high-resolution digital twins, and we also build the digital twin engine. So that's the center. Moving on a bit to our operational pipeline. So we receive observations from around the world. These can be from satellites, from weather stations, from sensors on aircraft, all kinds of places. We receive about 200 million observations per day. These then feed into our Earth system model, which runs at a 9-kilometer resolution. And this model is producing about 120 terabytes of data per day. And we have those 4 cycles I mentioned each day. So it's about 30 terabytes per cycle, and the cycle runs in about 1 hour on the HPC. As the data comes out of the model, we also do what's called product generation, which is kind of post-processing, generating refined products for our national weather services and our other clients. So these may be cutout regions, grid interpolation, basic processing on some of the fields that we produce. We then push these products out over the internet, about 45 terabytes per day, to a lot of destinations around the world. Now, I mentioned that some of this is running in a time-critical window. So except for the observations and the gathering of observations, pretty much this entire part of the workflow has to run in a 1-hour time-critical slot. Weather forecasting is quite interesting because the data we produce is incredibly valuable, but not for very long, because nobody wants to forecast for yesterday. So we have quite a lot of time pressure with our forecast. So from the point that we start running the model to distributing data to our members, the clock is ticking. Within this pipeline, we have quite a big I/O bottleneck. The Earth system model is writing out around 30 terabytes of data in that 1 hour, and we're simultaneously reading this back into product generation. We read back in about 70% of that. Those products that we're in right back to the parallel file system, where they then get distributed across the internet. We've tested how big an impact that I/O bottleneck is. If we run the IFS with no I/O versus running it with I/O, and then versus running it with product generation in parallel, we see that by running product generation in parallel to the IFS, we are increasing the runtime of the whole system by about 26%. In fact, it's not just these 2 components that are coupled by the parallel file system. Almost every element of the workflow is basically coupled by the parallel file system. Data is absolutely central to our workflows. And this is not just a performance concern, but also a data management concern. And this is some of the expertise that we're trying to bring into IOC, because we have quite a good system for dealing with the data management side of things. So at ECMWF, we index all of our data via scientific metadata. We have a dictionary of key value pairs, as you can see on the right, which describes the data in scientific terms. So we express the date of the forecast, the time, the type of parameter. We're not addressing data with UUIDs that belong to some S3 bucket or some complex file paths that don't mean much to anyone. It's a really important part of how we manage the data. This goes a step beyond just storing metadata with the data. So that's a very important step. You need to be able to describe your data, but we use that metadata to actually index and identify the data. And all of the data in our meteorological archive, about 400 petabytes of data, going back all the way to 1975, is all addressed with the same data language, the same basic schema of key value pairs that describe the data. This means that the data is implicitly discoverable and findable when you know the schema of your domain. So you can very easily find data from 30 years ago just by changing a few values in your query. You've probably done some kind of semantic data access yourself, whether that's storing holiday pictures or storing music on your computer. You've probably organized it with some kind of folder structure where you've put maybe the date of your holiday, where it was, this kind of thing. That's a pretty good start, but a more scalable implementation decouples that scientific identification from how the data is stored in the storage resource. So at ECMWF, all of our applications and tools talk using an API called the FTB or the Mars API, which understands this dictionary language where we have a set of keys and values, and it abstracts away from the user how those objects are stored in the resource. So we are free to store them in a POSIX file system in a different layout to how you might if you were doing it yourself. We can store them in different buckets and objects. We can put them on different memory locations, or we can put it to tape. And the applications and the scientists who write those applications don't need to care how the objects are stored. All they need to know is that language that they speak that is part of their domain, part of their scientific language. So going back to this diagram where we have the parallel file system in the middle, actually none of these applications directly talk to the parallel file system. They talk to an API which abstracts it away. And what this means is that we can actually swap out that parallel file system for other kinds of technology. We can explore NVRAM, we can explore hierarchical storage mechanisms and things like this. And we can seamlessly update all these applications to use these different kinds of backends. So the API I was talking about comes from a piece of software called the FDB. This is a domain-specific object storage. It's a transactional, no synchronization, and it understands this semantic data access to data. So it's effectively a key value store where the key is your dictionary of scientific metadata, which at ECMWF is the Mars language, and the values are byte streams, blobs of data. For us, they are GRIB messages. GRIB is a standard World Meteorological Organization file format for meteorological data. And the FTB then abstracts that layer of, the users just see the keys and values, and then FTB can support multiple backends behind that. So we currently use the POSIX backend, currently based on our Lustre parallel file system. We have a Ceph backend which uses librados, and we have an Intel DAOS backend under construction at the moment. And this is how we do it at our center at the moment, and some of the experience that we want to bring into IOC. We've successfully used the system in different EU projects. We had a project called NextGen.io, where we were exploring at the time very novel NVRAM technology from Intel. We had a prototype system with 34 sticks of 3 terabyte NVRAM DIMMs. And we were testing our performance there, and we could just take our workflow, basically swap out Lustre for an NVRAM backend and test the performance. So we did this. We tested the throughput of the servers just in doing pure I/O. We could reach about 72 gigabytes per second writing and about 60 gigabytes per second reading with over a distributed number of FTB servers. And what this meant in real terms, when we run our application, when we couple the model and the I/O and the PGen all together, we find that the model overall runtime was no longer affected by product generation. Basically, these NVRAM technology had solved the I/O bottleneck, and we didn't have to modify the scientific applications in any way. We just swapped the backend on FTB. So how does this all play into IOC? So IOC is bringing 3 main things that are interesting for us. It's bringing hierarchical object storage all the way from NVMe to tapes, which could be a very strong contender for meteorological data storage. It could potentially replace Lustre and NVRAM and other different technologies that we're looking at. We're also interested in looking at the ephemeral services and the data nodes to see if we can do in situ data processing for our product generation, basically exploring whether we can put that whole I/O read-write bottleneck into the hottest tiers of the hierarchical storage management and get better performance in that environment. And finally, the bit that we're contributing the most to in Work Package 5 is the data access and storage interface called DAISY. DAISY is basically our take on taking FDB and converting it into a domain agnostic piece of software that can be used by all sorts of other different scientific domains. So I'll talk a little bit about that first, and then I'll come back to our workflow. So DAISY is designed to be a scientist-friendly object store, which abstracts the use cases and the programmers who have to write those use cases from complex I/O systems, whether that's the I/O systems we build in IOC or whether that's other I/O systems. It's meant to be flexible. So DAISY kind of sits in the middle of the project. We have a front-facing API, which is the API that speaks the scientific language for the use cases, and also speaks that language to other I/O middlewares that applications are then built on top of, such as SciLib or MPIAO. And then behind the scenes, we have abstractions for how we actually store the data and interact with the data storage technology. So we have an index abstraction, which is where we store the mappings between scientific keys and the objects. And we have a data store abstraction, which is where we actually store the objects. Both of these could be based on Motor Cortex or the IOC HSM API or POSIX-based systems, or we can put anything back here, basically. We're trying to bring in what we've learned from eSymbolF over 40 years in building these data storage abstractions, but make it as a domain agnostic version, not tied to methodological data. So DAISY is domain agnostic, but you provide to it a schema which defines your domain. So you can build a domain for lattice quantum chromodynamics or cryo-electron microscopy, which will have different scientific keys and values, but in essence works the same way. By bringing this software to the wider scientific community, not just meteorology, we're hoping that we can build more collaboration in how the kinds of storage backends that we can develop, and we can share a bit of the development work in building these kind of backends. And the ultimate goal here is to bring the IOC HSM storage to the use cases in IOC in the most friendly way, but also to live longer than the project and keep fruitfully working with different use cases and different IO solutions to kind of build a platform where we can share IO expertise, basically. So going back to our workflow, so we've taken the 1 hour time critical window that I talked about before, particularly looking at this read-write bottleneck that we have, and we've built basically a simulation of this workflow that we can run on the IOC prototype systems. So we have our IFS model, that's our integrated forecast system. It's reading some initial data, writing the model output, reading it back in straight into product generation and writing those products out. And we also capture some of the extra IO that's going on, such as the archiving to tape. We archive all of our operational forecasts to our long-term storage. And we also have checkpoint restart files for the model that allow us to do error recovery, things like this. So we're capturing all of this at different tiers of of storage. So the initial data, model output, and products are all kind of temporary / campaign data, and then we also have longer term storage requirements as well. We can't actually run the IFS on some of the prototype systems we have. We dedicate almost an entire HPC to running IFS, so it's not really feasible. But what we do have is an IO simulator that's been built over years of profiling and testing our code, which basically mimics the IO output of the forecast. So our current system, we run an IO generator, whether that's the model or the simulator. We write to our FTB with a POSIX file system, we read back product generation, and we archive. What we want to do in IOC first is swap the FTB for DAISY. Then we want to swap the storage mechanism to the HSM. This gets rid of all the tiers of storage that we currently use, such as the luster and the tapes. And then finally, we want to look at how we can use the in-situ processing to optimize the read-write bottleneck in our workflow. That's kind of it. I just want to leave you with a few highlights. So we run time-critical weather forecasts, and they have an IO read-write bottleneck. we need to explore new hardware and software solutions, especially as our forecast increases. We're looking at an order of magnitude increase in data in the next 5 or 10 years. We have lots of experience with semantic data access and abstraction of data storage, which we want to bring to IOC with the DAISY software, and we're hoping to collaborate more with other scientific domains and other IO solution providers to build up DAISY into a really useful package for lots of different kinds of software. That's all. Thank you.
Thank you, James. Thank you for a nice description of your use case. Are there any questions for the audience? I don't see questions in the chat. Feel free to ask. Okay, maybe I have one. Okay, while implementing in your use case, while implementing the IOC approach, do you have some exact expectation regarding the speed up? Is something really what are you really interested in, or do you have some strong KPIs really defined you would like to achieve in this project?
I'm not sure if we have any exact numbers. We're interested in a few different aspects of it. We're interested in how the orchestration works and what benefits we might gain from that. We're interested in how the HSM can automatically move things between storage tiers, and maybe how that affects the process that we have of currently writing to disk and then copying to tapes and so on. We are, of course, interested in how much faster we can make it, but yeah, we don't have any expectations at the moment. And it will depend a lot as well on what resolutions we can run at and things like that. We obviously have numbers from our Lustre system. We'll have some new numbers from our new data center in Bologna. We've got numbers from the Next Gen IO project with different NVRAM and things like that. So it'll be interesting to see what the different hardware underneath also provides.
Okay. Thank you.
Thank you very much.
So if there are no questions, thank you very much. And we can now move to our second use case, which will be presented by Damien Chapman from CA, and which will be focused on modeling astrophysical systems by Ramses. Damien Chapman is an engineer researcher since 2014 at CAA, Saclay, France. He received a PhD in astronomy and astrophysics in 2011 from the Paris Diderot University in France. His current research activities focus on parallel scientific data analysis and visualization through development, adaptive mesh refinement data model, and data compression. He is also the core developer of the Galactica simulation database for astrophysicists. So, Damien, the floor is yours. We cannot hear you.
Yeah, can you hear me?
Yeah, now it's better. Yeah.
So I'm going to talk to you about the Ramses use case for astrophysics. So Ramses is an hydrodynamical code for self-gravitating astrophysical plasma flows developed at CA 20 years ago. So the first publication was in 2002. It's an open source code to model self-gravitating magnetized fluids with a community of around 300 users around the world. And in terms of publications in astrophysics, it's one of the 4 most used code in the field of astrophysics. It's written in Fortran 90. It's parallelized using mostly MPI and some versions of it, some additional OpenMP instructions. So it's written with about 50,000 lines of code. And the main characteristic of the Ramses code is that it uses adaptive mesh refinement technique to closely follow the flows of the of the model with adaptive resolution. So, for example, here in the two images that I show, you can see on the left part the gas density distribution of two colliding galaxies, and on the right part you see that the so this is the preview of the mesh of the simulation, so that you see that the resolution of the simulation follows the gas density distribution, with the finer cells where the gas is more dense. So in terms of I/O, historically the Ramses code used only custom POSIX files I/O scheme, with only one specific type of I/O output, which is only checkpoints data that are used for both restarting the simulation and for post-processing purposes, for analysis and visualizations. So the format is code-specific for Tron binary files, and the problem with Ramses is that it implements an I/O policy with n files per MPI process. So if we run a simulation with tens of thousands of MPI processes in parallel, we rapidly end up with a range of 40,000 to 80,000 files per checkpoint data written by Ramses simultaneously on the file system. So that, of course, leads to very drastic bottlenecks in terms of I/O. So in terms of applications, Ramses is used in the community for a wide range of scientific applications, spanning from cosmology to galactic dynamics. So here at the bottom left, you see interacting galaxies. At the top left, you see a cosmological simulation. Here it's at the bottom right, another cosmological simulations called Extreme Horizon. But we can also do interstellar medium modeling, stellar formation, planetary system formation, accretion disks, like in the top right corner, sorry, and a supernovae explosion in the interstellar medium. So it spans a wide range of applications. And so the I/O pattern of Ramses is quite peculiar, because one MPI process writes n files. One checkpoint data is written into one directory. So it's P processes times n files per processes. And one simulation is several snapshots, several checkpoints data. So it's n directories times P processes times n files. So we end up with very small files, typically less than 1 gigabytes, but that impose a great limit in terms of scalability of the IOs. That saturates above 8,000 MPI processes in parallel. So with the IOC, in the context of the IOC project, we already started, and we expect some future benefits in terms of both Ramses IO scalability improvements and improve post-processing productivity and data management policies. So first, we started with the integration of the Hercule parallel IO library, which is part of the work package 5 in the IOC project. So with this integration of the Hercule library in Ramses, we already started and managed to reduce the number of files, which of course ease the inode limitations on typical Lustre file systems in our typical use case with Ramses. With the possibility to contribute, for multiple MPI processes to contribute concurrently to a single share file with the IO concurrency, thanks to the Hercule IO mechanism. So with this, we already demonstrated the largely improved scalability of Ramses IOs over 8,000 MPI processes with the Hercule library on the Hierarchical Curie supercomputer at TGCC, which is a Price supercomputing facility. And we expect to take advantage of supercomputer storage architecture and potentially hierarchical storage system. Fortunately, the Hercule parallel IO library already implements a semantic approach similar to the one presented earlier by James. So it's completely compatible with the DASI interface. So in the short term, or maybe midterm, we can expect to have the DASI interface implemented in the Hercule IO library. So it will be seamlessly integrated into Ramses. And we also expect to reduce our data volume and improve our simulation data management policies with the help of the Hercule integration. So the pattern of the Hercule IO scheme, so we started by splitting the workflow in two separate parts. The first one is the checkpoint format, which is provided by the HPROT database format of the Hercule library. So this is only used for checkpointing and restarting the simulations. And we created another data flow concerning analysis and post-processing and visualization purposes. And this is made available by the HDEP databases in the Hercule IO library. So these two data flows can be done at very different frequencies in the Ramses workflow. And this is a great advantage because in terms of IO performances, there are a lot of differences. So the HPROT database is strictly dedicated to checkpointing and restarting. It provides basic binary storage. It doesn't need to be understandable by other code. Okay, it's only required for the Ramses code, and it takes advantage of asynchronous IO. So no additional memory cost because we don't do any copy of data. The HDAPE database, which is only dedicated to post-processing purposes, we implemented in this context an optimized data models for adaptive mesh refinement format. So typically for Ramses. So this one is self-described and understandable by other eventually post-processing analysis tools. And we can eventually restrict to subset of physical quantities if we're only interested in some of them and not all of them for post-processing purposes. It's lightweight compared to the HPROT database, and we have managed to implement some data redundancy removal algorithm and a very efficient data compression algorithm on this particular data model. So this is the first benefit of the Hercule integration Ramses. So if we get back to the Ramses workflow, typically, at the startup of the simulation, we intend to use typically the NFS ephemeral services to basically import startup data, typically initial condition files and very lightweight configuration files at the beginning of the simulation. Then the Ramses code initializes the entire adaptive mesh, adaptive resolution mesh, and then we only have to store on the file system using potentially the DASI interface, one or a couple of checkpoint data per 24-hour run simulation. And each time we restart the simulation and we need to read those checkpoint data, And so this happens only at very low frequency, but at higher frequency, we are able to write some backup data, so HDAP files, HDAP databases for analysis purposes, but much more frequently than we do checkpoint data. So eventually can be move around in the hierarchical storage system with potentially the use of data movers in our workflow description file. We are not clear yet on how to place, I mean, the hotness of the files we want to implement. And parallel to this simulation workflow, we can execute an analysis session in our workflow that will make use of this HDAP backup analysis data sets to execute some post-processing analysis, and eventually provide some potential feedback on the running simulation session to modify on the flow online the subgrid model recipes during the execution of the simulation round. So that's our workflow within Ramses. So if we want to make use of the NFS ephemeral service, that's only for very low IO intensive tasks, namely, as I said, reading initial condition files and configuration files, and write output log files. But that will be very low IO intensity. The most IO intensive part will take place on the DASI ephemeral services during our simulation run session to basically read or write checkpoint data or analysis HDAP databases with different data volumes in both type of Hercule databases. But these HPROT and HDAP databases will be done at very different frequencies. So in terms of I/O, it will be roughly the same I/O bandwidth in the end. And of course, to read these HDAP databases in our analysis session for post-processing purposes. So typically in our workflow diagram, like the one presented by Philippe earlier, this will be presented like this for our simulation workflow. So we will create a workflow session and we will run several steps sequentially, starting by the initialization step. And after the initialization step, we will run several 24-hour run restarts of the simulation and eventually check the status and run in parallel an analysis workflow. So that's it for the Ramses use case presentation. If you have any questions, I will be happy to answer it. Thank you.
Thank you, Damien. So this is a question to audience. Do you have any questions apart from whether 49 years ago? I guess James will answer separately. No questions from the audience. Okay, so also I have the same question for you. Is it possible now to expect some concrete speed up or concrete? Do you have some concrete expectations of speed up using this IOC approach?
We have not managed to test, I mean, and benchmark increase in terms of performance regarding the use of ephemeral services and data nodes yet, but eventually with the use of much lower latency data nodes, we'll expect some nice improvement on our IO bandwidth. But what we already managed to demonstrate is the great improvement in terms of performances brought by the integration of Hercule itself on regular rotating disks file system. On Lustre file systems. We managed to run some Ramses simulations on up to 130 gigabytes per second in terms of I/O speed on the Irene Joliot-Curie supercomputer during a Ramses benchmark with Hercule a couple of years ago already. But we expect to go even faster, maybe with the use of data nodes and ephemeral services in the context of the IOC project. Yes.
Nice, thank you. We have another question here. From Amir, does this project have a Git remote repository?
You mean a Git repository for the Ramses open source code, or for the? It's not on GitHub exactly, but we have our self-hosted GitLab server at CEA, which hosts the Ramses source code with the Hercule library integrated. Yes, it's a self-hosted GitLab. Yes.
Okay. So thank you for your presentation, Damien. Now we will continue with the rest of the use cases. And the first use case will be presented by Jiří Nováček from CEITEC, remote on-the-fly analysis and cloudification of cryo-electron microscopy data. Jiří Nováček is the head of the cryo-electron microscopy and tomography core facility at CEITEC at Masaryk University in Brno, Czech Republic. He received a PhD in biomolecular chemistry in 2013, and his current activities revolve around the automation of cryo-electron microscopy data acquisition and analysis. He also focuses on the implementation of new workflows which involve cryo-electron microscopy. So, Jiří, the floor is yours.
Thanks. And first, let me briefly introduce who we are, where we come from, and what do we do. So I'm coming from the institute called CEITEC, which is located in Brno. Brno is roughly 1.5 hour drive north from Vienna. And we are primarily focusing in our lab on providing services. So we're a service laboratory using electron microscopy for the life science research. One type of a study that we, for instance, can do and can provide are the structural studies of the bacteriophages. So you may have seen or heard that about the skin infection or skin blisters, which are caused by the bacteria called Staphylococcus aureus, which are may get difficult to treat by the antibiotics, which is a standard treatment, as these bacteria get actually insensitive against the antibiotics during the time. As an alternative, one can think about using bacteriophages, which are viruses of these bacteria. And one such bacteriophage is this 812 bacteriophage. that we can actually study and determine its three-dimensional structure of its individual parts using cryo-electron microscopy. So the goal of the cryo-electron microscopy here is to determine three-dimensional structure in order to generate ideally an atomic model of individual proteins that compose the structure of the bacteriophage, and using that, for instance, visualize the phage in different functional stages, like the pre-infection state or the post-infection state, and using the data, explain or infer the mechanism of the infection of the bacteria by the phage. Since electron microscopy data are the imaging type of a data, which may eventually be fairly large, as I will show later, our goals within this project is to facilitate the management of the raw cryo-EM data, so that we can annotate the data directly when they are produced, and automatically deploy them to the cloud solution, ideally a federated one, which will run a service that will take care of the data archival and subsequently data publication. In the ideal case, we will also analyze the data in the real time, not on the resources that we have available, but on the resources that are run by professionals. So, for instance, by on the HPC. So how do we collect data, and how do we carry out the analysis of the data to obtain three-dimensional models? So the object of our interest is a three-dimensional object from which we, when imaged, we obtain a two-dimensional projections of this three-dimensional object. And we take an image that is called micrograph. We don't care about the whole image, but we care about individual regions in that image, which we call particles or regions of interest. So we get the inherent issue with of the technique is its low sensitivity, and for the structure determination, we need a large number of these particles. That means that we need large number of the micrographs that makes the whole data acquisition or the whole experiment data intensive. During the acquisition and the analysis, we need to take care of issues like the sample drift or drift of the molecule during the imaging. Of course, the interference with the point spread function of the imaging device, in our case, the electron microscope. To obtain the three-dimensional structure or three-dimensional model of the molecule that we are imaging, we need an initial model, which can be actually a geometric model, and which we will reproject and compare these projections to individual particles from the experimental data that we collect. Because for each of these particles, we know that these are two-dimensional projections, where we don't know the projection angles of them. They're projection angles, which is the part or the factors that we need to determine during the data analysis. So we compare projections of our reference model, for which we know the projection angles, with the experimental data, and assign each particle the best match projection angles. And from that, we calculate a new model that will serve then as a reference from the next iteration. So it is the refinement of the three-dimensional model is an iterative process, which works on large number. This may be hundreds of thousands of individual particles, and to calculate the final three-dimensional model. And at this stage, the whole process becomes computationally intensive. So to describe the part of the data flow, so we collect the initial raw data, which are fairly large. So we collect roughly 2 terabytes of raw data per one acquisition session, which takes roughly 1 to 2 days. On that, we can run real-time data analysis to generate a pre-processing results that will already be significantly smaller. And on those, we're running the data analysis to first select only the particles which are suitable for the three-dimensional refinement, and finally refine the structure, the three-dimensional model. You can see that the eventual outcome of the analysis does not require does not pose large storage requirements. However, the original raw data are significant, taking into account that the microscope runs 24/7, and we are producing this amount of the data within 1 to 2 days of the data acquisition. So in order to facilitate the data analysis, we originally need to build a small dedicated computational resources very close to the microscope, and couple them with the storage resources that we've used for the data processing and analysis, and then finally use the another storage for the archival of the data, and for the publication of the data to the owner, to the user for the further analysis. Our goal within the IOC project is to change this strategy, as we are not experts in the data storage and high performance computing, and do the data analysis on the remote HPC resources, similarly and as well the storage of the data on the remote resources, ideally running some federated cloud solution. The solution that we are building within partly within this project then comprise the front end part that allows us to submit the data job into the system, so which then starts transferring the data from the microscope as they are generated real time to the HPC, where we run the data analysis, and the data are then deposited, stored on the storage close to this HPC resources, which may be coupled to the additional storage for the data archival. And the system should also will take care about the data publication either to the dedicated database or to the general database once the data analysis by the user is finished. For the connection with other applications within the IOC project, we see that the data analysis then by the user can be coupled with the DAISY that's been briefly introduced before. So far, we've managed. We primarily focused on the front end part and tested the transfer, the real-time transfer, and the real-time analysis on the remote HPC resources. So this part of the workflow is being built and finished. And of course, there are still processes that we need to finalize. So to once again describe the data cycle, we generate roughly 2 terabytes of the data within 24 hours. That means that we produce 150 megabytes every 10 seconds that are, once generated, transferred to the remote storage, from which we run the real-time data analysis. The original raw data needs to be archived together with the metadata, and the results of the data analysis are either stored for the data owner for the data analysis campaign, or are used as a feedback for the setup of the microscope, or check the data quality and potentially premature termination of the data acquisition if we find out through the data acquisition that we can stop the data acquisition earlier. Besides the original raw data, we also aim to archive the workflows, primarily in this case the real-time on-the-fly data processing workflow, and eventually the owner of the data will like to archive the final product, which is then published in the public database. This part then describes the front-end part. So we're relying on the web browser based application that we have prepared for this. That is either accessible from directly from the instrument that we have in the internal network, not accessible from the internet, or can be accessed from the outside using a certain identity provider. Sorry. The application has instrument-based specific setup, so we can set a different set of workflows for different instruments. We can define multiple workflows per single instrument, and we, in order to make the final data publishable under the FAIR principles, we are storing additional data model that combines 4 parts. It is the information about us, about who generates the data, the information about the user, so about the data owner, importantly the information about the sample that we are imaging, and then the information about the actual data. The application provides, communicates with the processing machine and provides real-time job status feedback, and I also have the user annotation by the email. So I can briefly show you how this such a job setup looks in this case. So we'll need to log in to the application using a certain identity provider. So I'll use my university. Now you should see different browser. Yes. So we'll just log in through a certain identity provider. In this case, I'll use my university. And good. Here I can select from which instrument. I have multiple instruments here, so from which instrument I'll gonna transfer and analyze the data, and what will be the type of the workflow I need. Then I'll select who will collect the data for whom. Myself as well. We define whether the user can be internal, external, and through which access route they come, so who pays for the access. Then we can we talk about the information that we store for particular user. Besides the name and the email, we also ask for the ORC ID to get a unique scientific identifier for our users, which then can be helpful during, or which will then be helpful during publishing and assignment of the data to the particular researcher. Then we can select the what kind of sample. I'll finish in this one. For the samples, we actually, as we are a service facility, we are usually accessed through a project, so we can use a project proposal that the user has submitted to access our resources to identify the sample, and then this project proposal will be again transferred within together with the raw data and stored and archived together with the raw data. And then we only need to define the name of the sample and particular keywords, which are later on used for within the public database to search through the data set that we've collected. And finally, we only need to find the data path on the instrument, set some parameters for the particular workflow, and run the analysis. And once the analysis starts, we will get a log window where we finally where we see the actual status of the data analysis. In the meantime, we also having then once the data acquisition is finished, the information about the particular data acquisition is stored currently locally on this web server as in a database of all the measurements that we carried out that carry the information down about the from the data model, and this database entry can later be used for the submission to the public databases. So if we go back on the instrument, we then see that the data acquisition is reports. If it reports problems, then it is directly the case for the operator to take an action, either with respect to the data or the data processing workflows. If not, you will get references on how the data processing is proceeding. Finally, we can stop the job and we'll get an email with a notification. So I'll try to go back to my original presentation. So to summarize, we're aiming and we have already developed a pipeline for automated annotation of the raw cryo-EM data and implementing the workflow for real-time transfer to the remote storage resources using Ioc federated cloud solution, where we can run the defined pre-processing pipeline in real time on the remote HPC resources, and we gather all the data that we will need for the publication, for its subsequent publication. So with that, I need to acknowledge, or I want to acknowledge my colleague Radek from SATEC, who is really involved in this project, and then colleagues from IT4I, Radek Furmanek, Martin Golasowski, and Jan Martinovic. With that, I thank you for your attention.
Thank you very much for your presentation. Thank you for interesting examples you showed us. So are there any questions? I cannot see the questions. No questions in the chat. Okay, maybe I have one quick question. You mentioned that usage of HPC resources. Did you already do some preliminary results? Are they promising, or is it too early to ask for?
Yes, we're actually now, or we've tested and ran the data processing on the resources at IT4I. And using a single node there, we get the same performance as we did with the 3 to 4 nodes that we have ourselves, which is given by the fact that you have the state-of-the-art technology, whereas ours was also significantly older than that. But and that I think is one of the major reasoning even for the future, because I believe it is expected that the HPC will gradually update its technology, whereas for us this is outside of the major scope, so to say.
Yes. Okay. Thank you. So if there are no questions, thank you very much. And we can move to the next use case. Okay. So the next use case will be presented by Eric Gregory for Ioc Supercomputing Center. And the talk will be focused on particle physics from a supercomputing number, QCD. Eric Gregory is on scientific staff at the Ioc Supercomputing Center in Germany. He received his PhD in theoretical particle physics from Syracuse University in the USA. His current research focuses on his current research focus involves performing large-scale computer simulations to understand how the interaction of quarks and gluons gives rise to the observed properties of hadrons, such as the proton. So, Eric, the floor is yours.
Okay, can you hear me and see my screen?
Yes, yes.
Okay, so I'll continue our tour of the diverse use cases of the IOC project with Lattice QCD. And as the title suggests, this is a numerical approach to particle physics. And so the plan of my talk, I'm going to begin with, I think, unavoidably a little bit of physics so that you understand the motivation of what we're doing. It's a little bit outside of everybody's intuitive experience. And I'll give you some physics without equations, and then a little bit of the method that we use in brief. And then I'll talk about the data challenges that we're encountering and expect to encounter as we move into the exascale era, and how we hope these to be alleviated with some of the solutions being developed in the IOC project. So let's begin with physics, and maybe with a touchstone that everybody's familiar with. We've all heard of, we all know about atoms. So I've got here a depiction of a helium atom that's about an angstrom across. And if we imagine it were to be blown up the size of a football stadium, then most of the space would be the electron cloud, and somewhere around the midfield line, we'd find the nucleus, which would be about the size of the seed of a grape. So if we then zoom in on that, and we find 100,000 times smaller, we have the nucleus that's, for most helium nuclei, it's composed of 2 neutrons and 2 protons. And we can zoom in yet further. And it's here we first encounter quarks, which is what we're kind of targeting in Lattice QCD. So a very simple picture of a proton or a neutron is that there's 3 quarks inside a bag, let's say. So a proton, we say, has 2 up quarks and a down quark. But a more, that's a kind of simple picture, and a more accurate way is to say, be a little cagey and say it's actually got the quantum numbers of 3 quarks. And by that, one of the most important quantum numbers that we're talking about is the color charge. So we're familiar with electromagnetic charge, but quarks have an electromagnetic charge, but they also have this we call it a color charge. And there's of course no color if you could see it, but it's named because it has this property that it can take one of 3 different values. And if you add a red value to quark to a blue and a green, you again get neutrality in the same way that if you mix 3 different colors, this red, blue, and green light. And all right, so a proton, I think I skipped this on the other pages. You'll hear me say the word hadron. A hadron is a bound state of is a particle that's a bound state of quarks and gluons, quarks being held together by the strong force, and gluons are the carrier of the strong force. And hadrons only exist in color neutral combinations. So you either have a hadron like a proton or neutron that has 3 quarks within it, all with different values of the color charge, or something like a meson that has a quark and an anti-quark, so it could have a red and an anti-red color charge, for example. So now we have a slightly more complex picture of what goes on inside a hadron like a proton. But to really understand it, we have to look at it from a quantum point of view. And so what's really interesting are these quantum field fluctuations that are happening all around these kind of main 3, what we call valence quarks. And these you can understand if you sort of picture pairs of quark anti-quark pairs coming into existence and then quickly annihilating each other all over the place. But at the same time, being able to interact with the valence quarks, with the gluons. So there's this sea of interactions and fluctuations happening inside the proton, for example. And to really understand the properties of a hadron from first principles, we have to be able to do a calculation that includes these quantum fluctuations. And as an example of the importance of these, we can go back to this original simple model that I showed you a couple of pages back and say, let's say we have a proton and our best theory is that it's 3 quarks in a bag and we want to predict the mass of the proton. Then it's kind of straightforward what we do. We take, if we know the mass of a quark, we'd multiply the mass of the up quark by 2, and we multiply, and then we'd add to it the mass of the down quark, and we'd get 9 million electron volts. And then if later somebody came along and did an experiment and they actually measured the mass of a proton, they would quickly find we're off by a factor of 100. And it's these quantum fluctuations within the proton that makes up the vast majority of the mass of the proton, and in fact, the vast majority of the mass of us and everything else around us. So we want to be able to understand where this comes from first principles. So why are we doing this? What do we hope to calculate? Well, as I said, there's some properties of hadrons that we can calculate, such as the mass, their internal structure, where does the charge lie, where is the angular momentum concentrated, how are they likely to decay if they're unstable, how are they likely to interact with other particles. Furthermore, we can predict the existence of states of particles that have not yet been observed in collider experiments, for example. But really the big question that motivates all this is, if we could do a very accurate experiment and measure some physical quantity, some property of the hadronic state, and we could, and then somebody else goes away and does a theoretical calculation from first principles using the best theory of particle physics we have, which is the standard model of particle physics, which includes the electroweak theory plus quantum chromodynamics. And so each of these will have some uncertainty associated with them. There's some uncertainty associated with an experimental result, and there's uncertainty related to theoretical predictions. And so then we come and compare the experimental result with the theoretical prediction from our best first principles prediction theory, if these uncertainties don't overlap to some reasonable amount, then our theory, the best theory we have, is insufficient to explain nature that we live in. So that would lead us to indicate there's a more fundamental theory beyond the standard model. There's good reason to believe that anyway, but also if we can understand the nature of any discrepancy here, then we kind of know where to look for the next generation theory of the universe. So that's what motivates us, and that's what we do. And then I'll tell you a little bit about the methods. So I've explained the chromo part is from the color charge and the quantum fluctuations. And so here's the lattice bit. What we simulate is actually a four-dimensional box of space-time that's got a regular discretization. So it's got 3 spatial dimensions and a time dimension, and we don't really distinguish with relativistic time signatures or anything like that. And then we populate this four-dimensional lattice with variables that represent the quantum fields for the quarks, and these live on the sites of the lattice. And there's some 3-component complex field. Actually, there's usually 4 replicants of it because there's 4 Dirac spin components we have to take into account as well. And then on the links in between these lattice sites, we have what we call gauge fields that represent the quantum fields of the gluons, and the gluons being the carriers that transmit the strong force. Now, the gluon fields that live on these links are 3x3 component complex 3x3 complex matrices. They're elements of the SE3 group, and so these are all the variables of our simulation. And as we begin, we start off with a lattice that's populated with random values, and then we do Monte Carlo updates, proposing changes and accepting them conditionally until we've generated a Markov chain of lattice gauge field configurations, we call it. So these are effectively, you can think of them as snapshots of all the different possible fluctuations of the quantum gluon fields under the influence of quarks that propagate around them. And so there's an algorithm to do this. We checkpoint these to disk, and these are quite expensive to produce, so these are saved for the long term. And then in the next phase, so that we call the hybrid Monte Carlo, or the HMC step in our workflow. And the next phase is to read these in one at a time and perform some calculations on these lattice gauge field configurations, using them as a background. And most of the calculations we do to try and calculate physical quantities involve calculating the solution to a very large, very sparse linear system. So we're interested in this solution vector here of a system whose dimension is the volume of the 4-dimensional volume of the lattice and times color and spin factors. And this solution vector we call a quark propagator. And then we can combine these vectors. So we do this on each gauge configuration that we've saved, and then we combine these together in something akin to a scalar product. We call it a contraction, and this gives us a type of correlation function we call a hadron correlator. And you see I've drawn one here where we contract together 2 quark propagators, and this would be if we were interested in studying a meson that has a quark and an antiquark. If we're interested in studying a type of hadron that has 3 quarks, like a proton or neutron, then we would instead contract three quark propagators together. And we can think of and be motivated to calculate sufficiently complicated things that we might want to generate many quark propagators on each lattice, and then they're combinatorial factors. So we might want to put them together in different small groups of 3, or if we're trying to look at a simple atomic nuclei, then we'd have to combine them in different ways so we get all the different combinatorial factors correct. And there's not enough memory in the node. So there's probably a stop to disk after we generate the quark propagators. We'll save them to disk, then reread them in for a separate step for these contractions. When we finally computed the hadron correlators, we averaged them over the entire statistical ensemble, and then do some fit to an equation that's motivated by physical theory, and the extracted fit parameters are related to physical quantities of interest. So there's this is our workflow in several kind of cartoony steps. Now we get to the data challenges. So we, as I mentioned, we have a 4-dimensional lattice, and we have every motivation to make this as big as possible. So for example, if we work with a lattice that has a volume that's too small, we're inducing some systematic effects because we're squeezing the physical system. Alternatively, it could be a small lattice that represents a big physical volume that we've just cut very coarsely, in which case we're inducing some systematic uncertainties related to a too large discretization scale. So we're motivated, bigger lattice size means smaller systematic uncertainties. If we run our Monte Carlo simulation longer, so we have a longer statistical ensemble, then obviously we get smaller statistical uncertainties at the end. And if we repeat the whole process with different at different points in the parameter space, it might be different quark masses or coupling constants, then we gain a longer lever arm to do a more accurate extrapolation to, for example, the physical point or something like that. So this again results in smaller systematic uncertainties. So we're incentivized to run as big a problem as we can possibly afford with our current algorithms and machines. And we're helped by the fact that lattice QCD is an extremely homogeneous problem. The data is homogeneous and the algorithm is homogeneous. We're doing the same thing all across this 4-dimensional lattice. And we have available to us many different levels of concurrencies and a very, and we've developed highly scalable algorithms. So the upshot of all this is that if you give us access to your machine, we will probably fill it up as much as we can. And to illustrate this, this is these different colors here. This represents the usage of the Joules machine, one of the flagship platforms at the Euler Supercomputer Center. And the different colors are different scientific domains that are doing simulations on the machine over a particular year. And what you can see on the bottom here, this lime green section that goes from about 8 o'clock to 4:30 is all lattice QCD. So even if you knew nothing about lattice QCD before today, we are using probably a good chunk of your computer. So how is that reflected in the I/O data? Of course, so just to remember, in the first step, this hybrid Monte Carlo step, we're checkpointing gauge field configurations, and which means these link matrices. So at every lattice site, where we have 4 dimensions of links going out, each one has a 3x3 complex matrix on it. So that's 72 reals per site. And this is kind of the current state of the art. People are running lattices that have 64 lattice sites in the spatial dimension, 128 in the time dimension. That's about 20 gigabytes of file, and you might want to generate quite a few thousand of these during the course of generating your ensemble. And then in the second step, in the spectrum step, we call it, when we're generating propagators, if you're saving those out, each one is actually 4 times as big, because it's a big kind of tensor that's got a spin and color index open at each end. And again, it's complex valued. So these we might generate 10 to up to 100 or so per configuration. And then at double precision, that's about 80 gigabytes of file. Yeah, and then of course, as we get faster machines and better algorithms, then the time between these writes or reads becomes smaller and smaller, and this is taking up, the I/O is taking up more of our time, obviously. So this is, you've seen similar diagrams like this in the other use case talks. This is sort of our workflow data flow diagram in a traditional storage hierarchy, where it's kind of a layer cake. The bottom is very fast storage that's closer to the compute nodes, but we can't keep our data there very long. Then there's some disks you can keep your data on for months or a year perhaps, and finally some slow tape storage that we put data on and just leave it. Here in Jülich, we have a relatively good connection to the sort of mid-range storage. So we checkpoint our purple blobs, these are the lattice gauge field configurations. When we're done generating ensemble, these are usually copied to tape storage and maybe even shared with remote collaborators. We try and upload them to shareable data repositories. But then when we go again to the next step of our workflow, we want to generate propagators and do some physics calculations. We have to move these back onto the disk somewhere, read them into the compute node, and then we save the propagators back on disk. And it might be we're doing some kind of simple calculation where the propagators can stay in memory, but otherwise we're putting them on disk and then reading them in perhaps multiple times to do these contractions before we finally get some correlation functions, these hadron correlators I talked about that can be analyzed offline. So again, as algorithms and the machines speed up, this moving data between the compute nodes and the disk is going to take more and more of our time. And there's also some human intervention that currently happens moving the data between these various tiers of the storage. And this is both of these things we're hoping IOC will provide us with a solution to as we move into the Exascale era. Okay, so as Philippe mentioned earlier, one of the things we have to do in order to get there is think about how we want to group our data into data sets. And one possible solution is just to put everything in one data set. So we're going to have a big temporary file system for this whole project. But we looked at the solution of having a different data set for every type of every category of data we have. So in this case, these little arrows represent the different steps of our workflow. So we have a workflow where we're generating these gauge field configurations, and these also have these different categories of data also have a different useful lifetime. So if we put all these in one data set, then we'll make that data set available for the second step, where we generate propagators that are stored in yet a different data set. And then this data set is useful for the third step, where we generate the hadron correlators. So we've already sort of mapped out how we think we're going to use this new technology. And there was a question in the chat earlier about whether it's feasible for the sort of non-specialist user to come up with these workflow definition file, workflow description files, and this new way of doing things. So we tried it. All the use cases have done this. We thought about which services we'll want to use. In our case, we have no interest in rewriting our IO library, so we'll just, at least in the first instance, use the POSIX NFS service and possibly the burst buffer. Some of this will work out as we do tests on actual prototypes. And we're interested in this DASI interface that James talked about, not necessarily coupling it directly to our IO library, because that's a lot of recoding, but as a way to manage, for example, the lattice gauge field configuration files that are a useful community resource, and we can categorize them by semantic keys like the coupling constant, the lattice volume, the quark masses that we input. But we use this as a standalone application in the first instance to try and organize our data after the fact. So knowing this, we set about kind of mocking up what we think we would do for a workflow description file. And just, I won't go through this in detail since Philippe already did, but remember there's a section here where we associate the the different types of services with the data sets, and then another section over here where we associate the steps of our workflow with the services. And so it's fairly straightforward. And then once you've got that, there's just a handful of commands that we have to invoke to first create these data sets and namespaces, and then populate them perhaps with some initial input files, and then start our workflow. So we've mocked up this, and we think we know how we do it. I don't think it'd be too big a burden on the user who's a scientist rather than a computer scientist. And that's where we are right now. We're kind of looking forward to the next few months, so where we hopefully can test this out on some early prototypes. So just to summarize that, as platforms and algorithms improve, we're going to be tempted to run naturally much larger problems with more elements in our statistical ensembles to reduce our uncertainties, and this will mean we have bigger I/O bottlenecks if we don't do something. So we're hoping this ephemeral service scheme that comes with the IOC environment will help us out there, and we expect to get some early results this year sometime on some tests. So I will stop there, and thank you, and maybe there's some questions.
Thank you, Eric. Thank you very much. So are there any questions? I don't see the questions in the chat. And we will move to our last use case. Ghazal Tashakur from Ioc University Supercomputing Center will present the I/O software for terrestrial systems modeling platform. Ghazal became a member of the Division of Computational Science in Ioc Supercomputing Center in 2021 as a postdoctoral researcher. She received her PhD in HPC and advanced simulation from the Autonomous University of Barcelona in 2019. Her research focus during the past years was the interdisciplinary experience in the academic and industrial investigation of distributed and parallel architecture patterns from grid to data visualization monitoring, open big data, and advanced hierarchical models.
Thank you. Hello, my name is Ghazal Tashakur, and I'm a member of JSC and collaborating with IBG3 group on TSMP Terrestrial System Modeling Platform in this project, IOC project. I tried to be fast, and as an introduction, I can say I'm trying to, okay. The terrestrial system modeling platform is a scale consistent, highly modular, massively parallel, and fully integrated soil, vegetation, and atmosphere modeling system. As you can see here, TSMP has complex interactions and feedbacks between different submodels and subsystems of a coupled geo-ecosystem model. And the linked energy, mass, and momentum elements transfer multiple spatiotemporal scales. Many other dynamics also, and different ingredients modify the land surface and ecosystem processes and show impacts in general. The capabilities of the fully coupled TSMP are presented through idealized studies on key hydrologic processes and their interplay with processes in the atmospheric boundaries. So in this case, for example, we have a first real data experiments over the Ruhr River catchment, which is presented. And since global climate and land use kind of changes inside global land use has an impact on water resources and their sustainable use and effects on the water security, the initial presentation of TSMP helps the scientists to better understanding and prediction of these extreme hydroclimatic events, such as heat waves or droughts. In compare of TSMP, in compare of individual approaches such as some observation which remain consistent, the climate models that do not include or highly simplified very land, water, and hydrological models, which usually simplify surface and subsurface. It could be a very complete and complex also model that some anthropogenic physical system like human water use also in local and non-local climatic effects can be seen and considered in this model. As it can be seen here, TSMP has three components models. The three components models, first is Cosmo, that recently improved and upgraded to Icon, and it's a small scale modeling, atmospheric model, and PowerFlow, which is a hydrologic model, and CLM, which is a community land model. And all of these three components coupled with OSS MCT coupler, and there is a data assimilation capabilities for parallel data assimilation framework. PDAF, we called it, here also helps the data, parallel data processing. TSMP is a multi-program and multiple data execution model, and this coupling providers has a different configuration and options for this different components model individually or combining to each other work together. And each of these component model can have different spatiotemporal resolution. TSMP publicly available on GitHub and owned by our group STLTS and also HPSC, Interesis, and PowerFlow also as a component model individually publicly available on GitHub and co-owned by IBG3. Cosmo available on request, CLM available on request, but we don't own them. And TSMP software has planned to development many different plans for development, and you can find different test cases, the new and the old ones available in DataPub. And current release is version 1.23 in total. TSMP interface and modeling frameworks uses in parallelism in a hybrid way using MPI, CUDA, OpenMP, MPI, OpenMP, and depends on the component model that you're going to use and integrate together. And the performance probability is also an ongoing effort, and mostly on PowerFlow. And we can run it heterogeneously and homogeneous in computing system, and mostly PowerFlow runs on GPU, and Cosmo CLM runs on CPU. The parallel I/O through NetCDF also it's a fully parallel for PowerFlow, and but Cosmo has a little bottleneck, and the performance analysis also exists, and on the hand continuously working on that. As a production, the features that TSMP has, which concerning impact I/O, that each model produces its output, and basically 3 groups of files, 1 per model, containing specially distributed model output variables generated, mostly NetCDF files, but we can use in other standards also. There are available standards, possibly in the model configured, and you can change switch. And also, I will not really under control of TSMP. So the features that affecting I/O are this complexity of different component models, different of the resolution of this component model, and also the time step that in total and differently should be calculated, and different output frequency and volumes also can be changed during the plan and the test case that you choose. I can show you a communication pattern between components in TSMP couple scheme for just one runtime, one step runtime. And here, these are ideal times that you can see between these internode MPI communications we have, while, for example, COSMO and CML are communicating, Perflow is on the idle, and when, for example, CLM is on idle, Perflow and COSMO are working. So I can say these, it can be seen that this coupling step during running time shows that these how this internode MPI communication became complex, and it makes the communication a little bit complex. Ensemble simulation of TSMP application is really important since we have a land atmosphere interactions in a European domain as a continental scale, and we have regional scale and local scale. So on local scale mostly works on groundwater, and regional scale, all of these as a forecast data data sets needs to be on some included in some simulation for TSMP, and the PDAF helps us for this parallel data simulation. The different data comes from different compartments of this model, and also handling how we handle the big data in this situation. Here, the challenges that we face in future, and right now, all these that concerning resolution and short output intervals, as you can see in the different model components, and because it's a model multi-physics fully coupled model system, so it makes it more complex, and increasing model domains and also the decomposition opposite of that in multi-scale processes is a very big challenge right now, and we need a very long integration times and on some size while we are checking the climate change on that. So the data flows coming, or the data flows paths are different, the modeling change together and impacts on each other, and data synthesis approaches and multiple data sets that we are using on it is a big challenge. And on the other hand, the legacy of the code, large codes that we don't own most of them. And right now we are trying on these challenges, and we propose solutions such as working more and deeply on the modular profiling to help us scalability, trying to improve parallel IO strategies and data staging with the help of IOC project, and to help to solve the IO bottlenecks we have, and trying to node-to-node finding tracing node-to-node communication for load balancing. And but the biggest one challenge right now is heterogeneous runs, CPU GPU runs, and the modular computing, and also data on data staging could be a very big deal. And post-processing step is on the now on we are working on that, and for in situ visualization and analytics. We chose Eurocodex 11 as a test case for IOC project because it's a long-term simulation, and it's from 1989 till the present time. It works for scientists. It's a high spatial resolution, and the typical runtime is 3 hours, so 45 all-time days, and the IO requirements, as you can see here, different individually for different component model, and in total could be 15 gigabyte nearly, and the boundary forcing data as an input data that you're using is near 3 gigabyte. And we are waiting for the future test case from Africa, that which is with higher IO throughput and very significant increasing volume of per output per model, and on the other hand, it's asynchronous, so it could be very more complex than the one that we handle right now. The experiments till now they had with Cordex was sensitive studies on 2003 for European heat wave and the evolution for the persistent conditions. Also, the probabilistic water resource prediction is the most important part of that they work on Eurocordex. Then we chose this test case for IOC project. That was the reason. In JSC, we are benchmarking TSMP based on Jube workflow, and this is our workflow that we propose to IOC also. We have as an input static files, very large static files that we have to download it from the sources, and the output should be used for analysis and for timestamp data sets, which we are going to send it to post-process and visualization steps. And based on these workflow that we propose to IOC project, we have 3 stages. We divided this workflow into 3 stages for IOC to divide it for the data nodes. And as you can see here, the input data set size and file count and output data sets that calculated shows that how big challenge we are in. So the most important part of that is to use ephemeral services. We have 3 stages, A, B, and C. A is pre-processing, B is the simulation pipeline plus ingestion step, and also the C is post-processing. As you can see here, we have a namespace. I think Philip explained at the beginning of the conferences, and in this condition, we stage B, this is showing you the stage B, all the simulation pipeline that individually for each component model created. Each component model has their steps in ephemeral services, and the ingestion of the POSIX outputs of each component model is going to DAISY. We count on using DAISY in this case because after this, when we get to the stage post-processing, the stage C, at the end we need perform some in situ post-processing and visualization, and we need on fly. So DAISY ingested data helps us better. We need a communication between DAISY and POSIX in this case, and this is the workflow that we propose to IOC concerning this. So we define a set of 3 ephemeral services for Cosmos, CLM, and Parflow, and using GBF services to receive these POSIX output from each of these component model. Then if each component model has output, this output should go, it depends on the decision, go to DAISY or directly to the in situ post processes. This is how we launched the TSMP IOC workflow in 3 stages. Is a sample that I'm showing, since I cannot show your YAML files. YAML files are really great. I couldn't show it here. So you can see that it's really simple to use these ephemeral services based on different steps that the TSMP has. I try to be very fast, and thank you for your time. And if you have a question, I will be happy to answer.
Thank you, Kazan. Thank you very much.
I tried my best, sorry.
Thank you. Okay, so any questions from the audience? I don't see the questions. Okay, so thank you very much. Well, we are approaching to the end of our webinar, so I would like to thank all of you who presented your talks. I hope that the topics were interesting for our audience. I would like to invite you to our next training events. As I said at the beginning, this webinar is the first training event of IOC project, and we are preparing now next ones for you. the next one will be held in December, 6th December this year. And it will be a hands-on workshop which will be done by Seagate, Cortex Motor Object Storage in IOC project. This hands-on workshop will be held at IT4I in Ostrava, in Czech Republic, but it will be a hybrid event, so you can join also online. But of course, if it is a hands-on session, hands-on workshop, it is better to be present. So, well, and also our next events. Another one will be done is planned for February. This hands-on workshop will be done by CEA and will be focused on Phobos object store on tapes. And the third one, this will be online webinar, and this is planned for April. This webinar will be focused on infrastructure monitoring tools and will be done by Bartek. So please stay with us if you are interested in these topics. Yeah, we will send you the information about our next events in a few days, because registration will start, I hope, soon. So, well, thank you very much for attending our webinar. I hope that the webinar was interesting for you, and have a nice rest of the day.